G'day everyone, welcome back after the Easter break. I hope you have had a great time. My name is Klaus-Dieter and I like to present today on the mechanical properties of materials, the course number 315008 in the spring semester 2022. So far we have talked about elasticity and plasticity and in particular on the dislocation theory. Today I like to split the lesson into two parts, so I will make two videos. And the first one is to finalize the plastic deformation chapter and talk about the strengthening mechanisms before we come then to the chapter number 4, the fracture theory. So here let's go into the strengthening mechanisms by dislocations. So what are strengthening mechanisms? The mechanical properties of a material, they are controlled by the microstructure. And we heard already the tensile strength is controlled by the work hardening rate. Means we plastically deform a material and then material becomes harder, it becomes stronger. And this is due to dislocations. The work hardening rate controls the amount of uniform deformation in the elongation or under elongation. The higher the elongation, the tougher the material and the greater the deformability. So that's the expansion of the strain stress curve. The ability of a metal to plastically deform depends on the ability of dislocations to move. So for plastic deformation, basically we need, or the major process we introduced here is the motion of dislocations. Reducing or inhibiting the mobility of dislocation enhances mechanical strength. In other words, if dislocations cannot move, we have higher strength of the material and the material becomes harder. There are four main ways of controlling the strength. Namely, there's the solution hardening, there's grain boundaries hardening, precipitation hardening, and work hardening, which is also called the dislocation hardening. Besides this, there are also other mechanisms of plastic deformations, which I have not discussed here much. There can be twinning, so the swapping and the flipping of crystallographic orientations on a habit plane. There can be martensitic transformations. There can be grain boundary gliding. And of course, there will be creep, which we discuss much later in this course. Today I like to emphasize on the dislocations. So how to achieve the highest strength? First of all, we can eliminate all defects, because if there's no defect in the material, like in the visca, in a single crystal, then we first have to nucleate a dislocation. And that nucleation needs to overcome some energy barrier. Crystals without defects and of very high strength have been achieved in viscas. Viscas are flaw-free materials with cross-sections of the order of a few microns, and they are some of the strongest materials produced by man. Some representative examples are provided in Appendix 1 of this publication, Strong Solids. There are iron viscas, for example, where the sigma experimental is 12.6 gigapascal. There's a patented steel wire where we have 3 to 4 gigapascal strength. Then we have the strongest bulk material steel is about 2 gigapascal. And most of the conventional steels, they have strengths in the megapascal regime. That is also shown here in the table to the right. where we list for various metals in a table format here, and on the logarithmic scale to the left, sigma u, the ultimate tensile strength in megapascal, and we see a large single crystal has a 2 tau 0 of 60 megapascal UTS. Then the typical cast iron is 275 megapascal. The mild steel, well higher, 400 megapascal. And now we come to the Maraging steels. So these are martensitic H steels in bulk form, and they can spread between the 400 and the 2500 megapascal. So here we go into the gigapascal regime. A fine wire can have 9700 megapascal, so 9.7 gigapascal. The whisker, 12.6 gigapascal. And the theoretical limit, I think for steel, is 20 gigapascal. We know the theoretical limit we don't achieve because we get dislocations. As said, the whisker is some of the strongest material, and this is because we have a relative thin wire-shaped crystal and need to nucleate dislocations at the surface. And if we look to the surface to volume or surface to cross-section ratio in the whisker, then we have a large surface energy, and therefore the nucleation of dislocations is large. The activation energy is large, so we get a high strength. And in the single crystal, once we have a dislocation in per area, per volume, the surface does not play so much a role, and that's why the large single crystals, they have a small UTS. If you compare it, so 1 over UTS times the elastic modulus, we get those numbers here, and there we see the smaller the better. So the strengthening mechanism is we create so many defects in the crystal that they interfere with each other. For example, dislocations. The principle behind strengthening mechanisms are the work hardening, the precipitation hardening, the solid solution hardening, the transformation hardening. In the work hardening, if we have a crystal or crystal light within the microstructure, then we get dislocations here, there, and eventually they interact with each other. We know they repulse each other or attract each other, so they align, and when they cross each other, also you need some energy to overcome. So eventually these dislocations, they entangle and cannot move anymore, or it becomes more unfavorable energetically to move. We also can put precipitations in to the crystal lattice. That means if then we have a dislocation line coming through here and moving in this direction, it cannot move over the precipitate, or it needs a lot of energy to go over the precipitate. Sometimes it has to climb. We know climb at room temperature is difficult. It has somehow to go around. Then we have solid solution hardening. We know we can have a solid solution, dissolve some impurities in the alloy. So if we have iron here, we can put carbon in, and then we have a dislocation. We know the carbon goes on interstitials. So the carbon will precipitate into the strain field of the dislocation. So it will accumulate around the dislocation, because if you expand the lattice, where you have a tensile strain, then you have more space in the interstitials, and that's where the carbon would go. So now, if you want to move the dislocation from there to there, you first have to overcome this cloud of solutes, which move by diffusion. So, by mechanical movement of the dislocation, by shear, you need to overcome now this widened lattice, which you may want to compress in the next state as the dislocation moves on. And that's more difficult because there's carbon setting. So it's harder to move. Then there's transformation hardening. We can have phase transformations. We can have martensitic phase transformations, I mentioned already, where we change the crystal structure. And others. Grain boundaries play a role. So the general rule, the strengthening of plastic deformation in crystals results from the restrictions of dislocation motion. We can restrict the motion by altering or promoting or adding the bond type. Yeah, if we have FCC lattice, aluminium, and then we say, okay, we take now titanium aluminium, then we have titanium aluminium intermetallic bonds, and they make the material stronger than pure aluminium. So you select the bond type. Then we have the dislocation interaction. This is the work hardening I mentioned already. Grain boundaries. So the grain size plays a role, because if the grain is smaller, you have more grain boundaries in a given volume. And that gives the whole patch relationship I will talk about. Solute atoms, I just mentioned in the slide before. Precipitates or dispersed particles. So you put something in where the dislocation has difficulty to go around. And phase changes. Transformation hardening or toughening of material. How does bonding influence the strength? So here in this schematics, in this table to the left, we have the weaker bond, and here we have the stronger bonds. We know already the strongest bond is the covalent solid, like in silicon, like in gallium arsenide and so on. Then I mentioned the intermetallics, titanium aluminide. This is between the metal and with some covalent characters between. Then weaker, we have the ionic solids. So it's not the bond which plays a role, but the electromagnetic repulsion and attraction between dissimilar and similar ions. We have the close-packed metals, which are the weakest, because these are just spheres which are packed together. And then we have the other metals, which may be a little stronger than the close-packed metals, because close-packed is just the spheres. So here, in the close-packed, which is FCC and HCP, hexagonal close-packed and face center cubic close-packed, the bonds, they are essentially non-directional. So the dislocation motion is easy. And here the examples I mentioned already, particularly FCC metals, aluminium, nickel, silver, gold, all your favorite metals. The other metals, so we have somewhat directional bonds and interaction. That's why they're not close packed, like iron, the BCC iron, other BCC metals. So there's a reason why they are not close packed. If they would be spherical, then there would be an isotropic, there would be close packed. So they have some directional character or some nearest neighbor interaction. So then the dislocation movement is relatively easy, but strongly dependent on the temperature. because there are various energy landscapes in the bonds. Nearest neighbors, second nearest neighbors. Second nearest neighbors play a role. The ionic solids, the bonds are non-directional, but the slip is directional due to the electrostatic attraction between unlike ions. So you don't want to bring a positive ion with a positive ion together. They repulse each other. Means when you do a slip, you have to conserve the electric order, the charge order. Otherwise, you may get repulsion and that costs a lot of energy. So there are less slip system, and that means the dislocation motion is difficult, because sometimes locally you have to overcome some of the, or introduce some disorder. And of course this is sodium chloride, cesium chloride, kalium, potassium chloride, and so on. Then we have the intermetallics. Titanium aluminide is here, nickel aluminium, nice shaped memory alloy, nickel 3 aluminium, titanium 3 aluminium, copper 3 gold, gold 3 copper, and so on. There the dislocation motion is difficult because again we have some directional bonding, we have the order, we have to break this directional bonding, we have to break the order, introduce this order, and especially titanium aluminide, out of the many different stoichiometries of titanium aluminium, there's titanium 3 aluminium, there's the titanium aluminoid, there's titanium aluminium 2, there's titanium aluminium 3, and so on. So many intermetallics in this system. In particular, titanium aluminide has a very high ordering energy. So if you introduce dislocations, you introduce disorder, then it costs energy and makes the material hard. So hard to move dislocations. And the covalent solids, we know that silicon, diamond is a hard one. Every lady has it, I hope so. Aluminum oxide, silicon carbide, silicon 3 nitride, gallium arsenide, and so on. So let's look to the general model for strengthening. There's a nice reference I gave here by Alan Brown on strengthening mechanisms in crystal from 1971. And you consider a slip plane here that contains a random array of obstacles. We don't care at the moment what the obstacles are at this point. So we have the obstacles, which are the blue dots here on the slip plane. And then we have this dislocation line. So imagine you have a dislocation line here at the bottom, which moves up here in this direction by applied shear stress tau, and eventually it hits the obstacles. So it gets pinned at the obstacles, and between the obstacles it can move forward, but it still remains pinned. So the dislocation line becomes longer because of the curvature. It bulges out. It wants to go in the direction to the top here of the graph. It bulges out, it gets curvature, it gets angle in between. So we need an extra work which is required to move the dislocations through the array of the obstacles, and this results in a higher stress to cause the flow. You can do that quantitatively now by looking to the effective particle spacing, critical angle to which the dislocation bends prior to the breaking away from the obstacle. So when we have an angle, eventually if it becomes too sharp, then the two parts get together again, and then we have a new dislocation line and probably a ring of dislocation around the obstacle. So let's tau be the shear stress equal the flow stress required to move the dislocation through the array of obstacles, as shown here. This allows us to define stress in terms of the strength of the obstacle that is inhibiting dislocation motion. So strong obstacles resist the dislocation motion, and the weak obstacles provide little resistance to the dislocation motion. If you only have a vacancy, which may be an obstacle, has a little crystallographic potential there for the dislocation, but it's relatively weak, so dislocation just moves through the obstacle. Or if we have one solute atom, it's also relatively weak. But if you have a big particle sitting there, then it's really hard for the dislocation to go around. Here's a summary of the hardening and strengthening mechanisms for crystalline solids. Again, we have the typical aspects here: the work hardening, the nature of the obstacle, there's other dislocations. So dislocations and other dislocations, they repulse each other, they entangle each other, they may interact with each other, attract each other, and it's relatively strong. And the hardening law is the delta tau to increase the hardening, the shear stress from the undistorted material to the hardened material, so we call that delta tau, equals alpha, some constant alpha. Here alpha equals about 0.2 for FCC metals and about 0.4 for BCC metals. So this is some constant we can calculate or estimate or empirical. Then we have the shear modulus, of course. We have the Burgers vector. For larger Burgers vector we need larger shear force. And then it goes with the square root of the dislocation density rho. So rho, somewhere here, is the dislocation density. You see that here. And this you can visualize or imagine. Square root of the dislocation density rho is something like 1 over the spacing of the dislocations in the linear scale. Then if you look to the grain size, we call that the Hall patch relationship. The grain boundaries play a role, and this is also a strong factor for hardening, and delta tau becomes then a factor divided by the square root of the grain size. That means we make the grain size smaller, basically there are more grain boundaries, then the material becomes harder. So K, what is K here? Scales with the inherent flow stress and or shear modulus, therefore K prime Y is generally greater for BCC metals than for FCC metals. So this is a scaling factor which we may consider. Then solid solution strengthening. The obstacles are just the solid atoms distributed over the crystal lattice. And that's relatively weak. I said already, if there's one point defect, the dislocation can move it. It feels a little bit. In diffusion, we know when we have displacement and there's this coherence factor that the vacancy wants to go back to the original location because of the strain field, which has to move with the solid atom, or the other way around. If there's a solid atom, then it interacts with an applied stress field. And that can be seen or described by delta tau becomes C. Constant C depends on specific mechanisms, so it's a constant. Shear modulus, strain to the 3/2, and then square root FR over B. So F is the precipitate volume fraction. precipitate radius. I'm sorry, I jumped already here to the deforming particles. So deforming particles is where we have small coherent particles, such as Guignard-Preston zones and theta precipitates of copper in aluminium. They are also relatively weak, so that goes with precipitate volume fraction times the precipitate radius divided by the Burgers vector, square root of it. Back to the solid solution, sorry I messed that up. The G, the delta tau becomes G, epsilon to the 3/2, C to the 1/2, and divided by 700. C number 4, equation apropos to substitutional atoms, parameter epsilon s is empirical, reflecting a combination of size and modulus hardening. So you don't go too much into that formula. And then we have the non-deforming particles. These are large incoherent particles. So you put some glass bulb, glass spheres or whatever into the aluminium or something similar, just an example. And that can be strong, and it depends on the size, L minus the spacing and between the precipitates on the slip plane and the radius. So this is a characteristic tensile stress strain curve for a single crystal. We have stage 1, then we have stage 2 with a larger slope, and stage 3 with a smaller slope. Characteristic tau versus gamma for single crystal depends on crystallographic orientation of the stress axis. Of course, yeah? We have had the Schmidt factor. And there are 3 stages of work hardening for single crystal. Stage 1 is easy. So we have the glide. Then we have the stage 2. This is linear hardening. So here we don't have many dislocations. So once we introduce the dislocations, it costs some energy. That's why it's steep, but then it flattens. So it remains flat. We introduce dislocations and they just move through the crystal and don't interact with each other. When they start interacting with each other, then the material becomes strongly harder. So we have a steeper slope, and eventually we call this here parabolic hardening in stage 3, where we have hard material, much harder than in stage 1, but the hardening does not accumulate anymore. It's somehow saturated. The same in this figure here. Stage 1 is the easy glide, single slip system. Stage 2 is with high constant hardening rate, multiple slip systems nearly independent of temperature strain rate. And then the stage 3 is with decreasing hardening rate. We have the cross slip and very sensitive to temperature and strain rate. And this is because we may need some climb of dislocations, and as you know, the climb of dislocations to go around each other. But in this big entanglement, this spaghetti, to go around each other, you need diffusion, or may need some diffusion aspects. So if you go to a higher temperature, it may become much easier than at lower temperature. The ability of a metal to deform depends on the ability of dislocations to move. That's what we're talking all about. And restricting dislocation motion makes the material stronger. Not so much new here in this slide. Ordinary ductility is sacrificed when an alloy is strengthened. Also evident, right? Originally ductility, I would say, is sacrificed when the alloy is strengthened. So let's look to the restricting dislocation motion by grain boundaries, strain hardening, solid solution, and composites. Let's go to the grain size effect, where we look into the pile-up mechanisms of dislocations. So, basic question is, how does a continuous polycrystalline material fails, which has no holes, voids, etc.? We get here the introduction of dislocations, maybe also twin planes, and they accumulate, and eventually you get these micro cracks or nano cracks here, where you have accumulation of dislocations. And then these planes or regions of high concentration of dislocations, where it becomes very hard the dislocation to move. So if you further apply shear stress there, then it may lead to crack. First nano crack, and then they can grow to larger macroscopic cracks. So we need to accumulate the dislocations here in the grain boundary. So let's say this is a grain, and it has a typical diameter D. And if you put a Frank Reed source here, you know the Frank Reed source, which expulses dislocation loops, and these dislocation loops, they move out, and they move out, and the next one follows, and the next one follows. How far can they move? The first dislocation can move until it hits the wall, until it hits the grain boundary here. Then the next dislocation comes. It lines up behind the first dislocation, either 90 degree or 45 degree, depending on the sign of the dislocation. So they attract each other and they line up in the lines. We have seen that. Yeah, these dislocations walls. We studied that maybe 2 lessons ago. And how far can it move? Well, until it comes close to the first dislocation. If it comes too close, then the energy of the 2 dislocations becomes larger. If you put one dislocation with double the Burgers vector in, it becomes 4 times larger as the energy increases with the square of the Burgers vector. So if you put 2 lattice planes together, then the Burgers vector would be 2b, and the energy would be 4 times the energy for one dislocation. So it stops moving towards the right. If you put the shear stress like this, they move all to the right here. And it piles up behind there. Then the next one comes, the third one, the fourth one, fifth one, sixth one. Then here we have others. They are like airplanes flying into the airport, and then they all come to the terminal here. So they line up. Now, this is the obstacle. So the obstacle in a grain typically is the grain boundary, as shown here. And these dislocations, they push, of course, on the grain boundary. They push so hard on the grain boundary until they can go through or introduce a dislocation in the neighbor grain. So there's some big energy barrier, but eventually it can go through, introducing a new or continuing the dislocation in the next grain. So one dislocation moving there may not have enough energy to penetrate the wall. But now, if the second dislocation comes and also pushes to the right, it wants to move to the right, it would lower the energy, that's why it moves. So it builds up a force. The force is given by the first dislocation pushing to the wall. Here, And then the second dislocation, pushing the first dislocation, pushing to the wall. So, two people pushing gives you twice the force. And then the next one comes, gives you 3 times the force, 4 times the force. So, it gives you many times the force until I can go through the wall. Let's say I cannot go through the wall. How many dislocations can I build up? Right. In the ideal case, I put the Frank Reed source into the center, or in average, I put it in the center of the grain. I can put it here to the left, then to this side I can accumulate more, and to the left I can accumulate less. But let's say we put it in the center in average, yeah? Average over many grains. Then I can put this number of dislocations in, namely the spacing of 2 dislocations times the number of time, or divided by the distance. The distance divided by the spacing of dislocations gives me the number of dislocations I can put in this half diameter. So I put half diameter to the right and half diameter to the left. And the same to the top and the bottom. So many dislocations can pile up. I have here the source at a given length L. And then how many can pile up? The minimum distance here, L divided by the minimum distance of dislocations, which you see here, here everywhere, yeah, there, you see these pile-ups. And then you have so many dislocations pushing onto the wall. So if you have a number n of dislocations in a pile-up of the length L at a planar boundary, then we remember that tau is proportional to G times B over R, and we construct this giant dislocation of many, many Burgers vectors. Then we get n times GB over L. So here we have, it's not a radial function anymore, it's a linear function, so it depends on 1 over L, not on 1 over R, and it's decorated by these geometric terms. Pi times 1 minus nu times L in the denominator. But you see this is a proportional GB over R, and now we have G n times B over R, and then the geometric factor is pi times 1 minus nu over L, because now it's not spherical anymore, it's elongated. So if you would do the mathematics, it looks like this. And that gives you an extra shear stress. So tau minus tau 0. Tau 0 is to move the dislocation at all. So that's a threshold energy, threshold shear stress. And then it becomes larger. And how much it becomes larger is given by G times n times B divided by kind of a radius, kind of a linear dimension, which depends on the shape. And of course, if you compress there in one direction, in the other dimension we have Poisson's ratio. And then n can be written as L times tau minus tau 0. So put the L here. N. Then we have pi times 1 minus nu divided by G times B. So mu equals G. This formula have been taken, copy and pasted from different sources apparently. Mu equals G. So the slip is transmitted across the barrier when the stress concentrations at the pile-up tip exceeds a certain stress tau star. So n times tau minus tau 0 becomes tau star. So when the applied stress becomes larger than the critical stress tau star. And now we can solve this. So we have tau equals tau 0 plus tau star GB over pi 1 minus nu L and the square root out of it. So tau becomes tau 0 plus, and now we put a constant alpha, we put everything in the constant alpha, times the diameter. So the L is proportional to the diameter, and all the other constants we also put into the alpha. So tau star GB over alpha D and the square root of it. And this is Hall patch strengthening, where the shear stress goes proportional to the square root of 1 over the grain size D, grain diameter D. I've shown it here in the table, not shown, but now I showed it. So delta tau equals K prime over square root of D. So we put everything else into K prime Y. And what we put in here basically are those constants. So we can plot it. The equation is here again. So tau equals tau 0 plus K over square root D. And this is the whole patch model of grain size average, or D is the average grain size. For copper, 70% and zinc, 30%, brass alloy, the data is shown here. So this is literature data based on experiment, and we see here is the square root of 1 over D. So square root 1 over D, and that has a very linear behavior. Here's the yield strength in megapascal. So here's the yield strength. If we go to 0, then we have the initial yield stress tau 0. So if 1 over D or 1 over square root D goes to 0, that means the grain becomes big, big, big. So we don't feel a grain size effect anymore. Then we just have the deformation strength of a single crystal, of a large bulk single crystal, which is weak. And as we make this grain size smaller, we see it linear increases with 1 over the square root of D. This is Hall patch model. And it applies for large class of materials. So the grain size strengthening is, here's another model. So we have the slip plane there, we have the grain boundary, and we have to bring this around the corner, and this costs energy. So you see they may pile up. Here we have one dislocation here, it piles up. The next dislocation piles up there. And if you do that further for many, they all pile up here like a traffic jam. And eventually some are transmitted through the grain boundary. And the next pile up is here. So the grain boundaries are barriers to the slip, and the barrier strength increases with the misorientation. This also makes sense. If there's a big misorientation angle, then it's difficult to get to induce a grain or a dislocation on the other side. And of course, as I've shown, smaller grain size, there are more barriers to slip, which leads to the whole patch equation. So the yield strength equals sigma 0 plus ky divided by square root of D. Dislocation grain boundary interactions. So the grain boundary impede motions of dislocations along entire lengths of dislocation line. Expect the grain boundary to be more efficient at pinning than dislocation obstacles. The stress to activate dislocation motion for a given grain increases with the number of dislocations pile up at the grain boundary due to the stress concentration. So that resumes a little bit what I've said, what I explained in the slides before and in words. So for infinite grains, the yield strength is intrinsic value of the single crystal slip. Yeah, infinite grain size is here. Then we have the threshold stress, shear stress we need to apply to move dislocations at all. It's not zero. And then for finite and decreasing grain size, the yield stress increases, as shown. Here's this dislocation pile up. I mentioned there's a Frank-Reed source. So Frank-Reed source, I've shown this schematic movie where you create dislocation, a dislocation loop. It may go down somewhere or it may be pinned to something. And then it increases. And in the next cycle it increases further. Eventually these two parts, they grow together. And we have one loop here in the plane. Then it increases. And as these dislocations now move towards the grain boundary, they pile up, as shown before, as demonstrated here again. So eventually that pile up gives a force, or it gives also back pressure. It gives a pressure or shear stress annihilating the external applied shear stress, and that makes a Frank-Reed source to stop. So Frank-Reed source stops emitting dislocations when the back stress caused by dislocation loops becomes sufficiently high to shut down the source. Yeah, dislocation cannot move to the right anymore, or on the other side to the left anymore. Then no new dislocations would be created in the Frank-Reed source, and it would shut down. Right. So we have these super dislocations here with the Burgers vector n times b. Then we have this decoration factor in the denominator. Tau 1 is the yield stress, or the intrinsic stress plus hardening stress is the applied stress. And this condition determines the number of dislocations generated. So the number of dislocation is here, generated by a source which can be estimated, and I think you will have tutorial and homeworks on this. So we have the friction stress, we have the back stress, and that becomes GB NB divided by 2 pi d over 4. So the grain size strengthening is shown here again. Physical picture. We get a force F star. So the force F star is n times the Burgers vector. So n dislocations, they push on each other. So here 3 of them, they push each other towards the wall, times the shear stress, or the difference, the exceeding shear stress above the natural stress, intrinsic stress, and that becomes then pi d over 2g. And from this force we can estimate now the number of dislocations in the pile up of the super dislocation is pi times d times tau minus tau star, so the exceeding stress over the intrinsic stress, divided by 2gb. Again, grain size strengthening. If we look to various data here, so we have a fracture stress, we have a yield stress, this is a fracture stress, and strain to fracture at minus 195 centigrade. This is here. So we see there is a temperature dependence of the strain to fracture at room temperature and at low temperature. And there are the different points shown. For example, here, very low, we just hit the yield point and then we fracture. This is brittle material. Then there we have some plastic deformation. So it yields and we have this nice hole patch behavior. And then we get the necking or so in a engineering stress curve. So it flattens up, it flattens. So yielding, resulting a crack is at low temperature. Here more about hole patch. So we have the 1 over the square root of diameter here and the applied critical stress. And we see for the many materials they behave very well to the hole patch law, hole patch equation. So we get these linear fits to the data points. Here we have 1, 2, 3 data points. Here we have some data points. Here we have 4 data points. Here we have many data points for the different materials. And you can work it out here. So we have the 304 stainless steel is here. 2 is 304 stainless steel, which is rolled. So the annealed one has less stresses. But if we have a rolled steel, then it has work hardened already. So we have already dislocations in the material, and then we add further dislocations by our tensile testing, for example, and get this slope here. Brass number 3 is there, so brass is much softer. Copper number 4, copper is very soft, we know that, particularly when it's annealed, but it behaves well, the hole patch behavior. So there are tables when you design a workpiece and when you design a microstructure for making a workpiece. Then you have the sigma zeros here given in megapascal for all of these materials, and the K. So typically the K, the KY as we call it, is shown there. So you can put it into this hole patch equation and get the yield strength as a function of grain size. So this figure again shows an example. I don't know what material it is, but the hole patch plot here, the length in millimeter to the minus 1/2, so 1 over square root millimeter. That can be the diameter of the grain, and the yield stress here in megapascal. So for very small numbers here, and we have the length in millimeter there, so here 1 over square root millimeter, and the top scale shows the length in millimeter. They're both logarithmic scales. So if you have something like 100 millimeter, this is a big single crystal. So here we have, this is 1 millimeter. Yeah, this is 10 millimeter. So if we have big bulk single crystal, we now we have the yield stress, the internal yield stress. But then, as we go into this regime of, let's say, smaller than 1 millimeter or just half a millimeter or so, to a few micrometer, so 10 to minus 3 here, millimeter is 1 micrometer. In that regime, we have this linear behavior on that scale. So this is a normal whole patch regime. And as we go to smaller grains or larger 1 over grain size here to the square root, if we go to smaller grains, you see here 10 to minus 6, this is a nanometer. Nanometer grain size, then we don't get dislocations inside because dislocation already makes up more energy than the surface energy, and it will be pushed out. So then we get a saturation again towards the theoretical strength of the material. So let's look more into work hardening. If you have many dislocations, we can make this model here. The shear produced by the passage of many parallel dislocations, then we get steps at the surfaces, which are each time 1 Burgers vector. And we have many of those steps. Of course, sometimes we can have 2. We call that the Taylor model of interactions among dislocations. And that gives us the following plot, namely we have here the shear stress in megapascal and the dislocation density per square centimeter, and see this linear behavior. So also it depends how many slip systems we have. Just for 1 slip systems, we get the round points here. There's 1, there. Then 2 slip systems, triangles to the bottom. 6 slip systems, triangles to the top. And polycrystalline materials, we have these squares here. So this is an average dislocation density as a function of resolved shear stress for copper. We have the yield point phenomena. So if we have an annealed material, say annealed copper, then we get a sigma yield 0 for the first strain stress testing. So we go up here, this is elastic behavior, then we go plastic, and then we unload and end up here. So this is our plastic strain as we know, and we call that, we count that from 0.02. So if we don't unload and we continue further from the 0.02, this is just a convenient number so that we can estimate when it starts to yield. So we call that point sigma yield 0. And then we unload here, and then we take the material and do the same strain stress curve again. Then it would not follow like the first one here, but it follows higher up. So it follows approximately the point where we have interrupted. That means it depends whether I take a workpiece which has been annealed, then we get sigma 0, or which has already been work hardened, like the rolled material, rolled or wrought material. Then I get a higher yield point than sigma yield 0. So the new yield strength, sigma yi, is higher than the initial yield strength, sigma 0. And the reason for this effect is strain hardening. Of course, now I can be smart, I can say I do this curve, I unload here, then I anneal at this point, then I would reproduce here the first curve again. So I would get sigma yield 0. But once we unload the dislocations, they remain in the system. And then we load again, so these dislocations are already in the system, and therefore the material is harder. So sigma yield the second time is higher than the sigma yield at the first time. So after the ice time, it becomes harder and harder and harder. That we see here, the work hardening. We call that work hardening. When we work the material, it hardens. So the first curve may be like this, elastic, and then we get plastic deformation here. We get the UTS and then it becomes weaker. So here we get work hardening and then UTS. Then in the second step, when it's already cold work before, like rolling or drawing, if I have a little work hardening, then I get a higher yield strength here and eventually go through the UTS and necking it down. And so on. So with more and more work hardening, I get higher initial stresses, yield stresses. But then the distance to the UTS is not that high anymore, because eventually, if I go this direction, this is initial percent cold work, but when I pull here, this is also kind of cold working. So the plateaus, they may go up a little higher because of the, depends how I cold work it, but not so much, not so dramatic anymore. Now here microstructures of iron, which has been cold worked to 20%. So we see a lot of dislocations already inside there. Or at 0%, we see these big crystallites with very few number of dislocations. There are always some dislocations in. So the stress, which I can apply, is proportional to 1 over dislocation spacing, which is proportional to the square root of the dislocation density. That's another interesting phenomenon here, the Lüders band. So we have the perfect crystalline material, annealed polycrystalline material here, and then we pull, so we get elastic strain and a yield. Then it yields, and when yielded, it becomes weaker. It becomes weaker because here in that low carbon steel we have carbon atoms sitting at the dislocation. And that's what I said before, with solutes you can have segregation of the solutes, or segregation of the carbon in the strain field of the dislocation. Because if I put the carbon here, it takes more energy because there's less space. Here also less space. If I go far away from the dislocation, this and this is the same. But in the vicinity of the dislocation, there's more space on this side of the dislocation, less space on that side of the dislocation. But more space, rather than in the average crystal structure, is close to the dislocation in the tensile stress field. So the carbon goes here. Now if I want to move the dislocation from here to there, if I want to move it there, then I need to compress this cell with the carbon inside and get the larger cell there. And that costs energy because I need to compress the carbon. So I need to overcome this energy to compress the carbon. And then the dislocation can move freely. And the carbon we leave behind. So that's what's happening here. I need to overcome this extra stress to compress the carbon, this stress amplitude. And then once the dislocation is moving, yeah, then it's moving, then it becomes easier again, because I don't meet carbon atoms. And that can happen by an area which is unyielded and which is yielded. So eventually I have here the unyielded material in white and I have the yielded material in gray. But then we know as we yield and as we propagate epsilon, the extension, we get work hardening in the gray area. So if work hardening becomes higher than moving away from the carbon, then I move this front inside. And here also move the front inside and inside. So leader's band can nucleate anywhere, can nucleate at the borders, can nucleate in the center. But here we see this unyielded area becomes smaller and smaller, unyielded volume, because I get work hardening in the already yielded gray areas. And that goes until here. That strain is when all this white area is consumed. Basically when the two gray areas, they touch each other, they meet each other. And then I do the normal work hardening. So first step, need to overcome the barriers by the segregated carbon atoms. Then I have this yield front in the real space, yeah. They move together until the whole material is yielded, and then I get the conventional work hardening. So that's called a Lüders band. One of the gray areas, a Lüders band. So what do we have here? Same thing. We get here the upper yield limit, the lower yield limit, and then we do work hardening until here. We unload and we load. We just continue the curve here as discussed a few slides before. Then at point Y, let's unload again. And now we wait. So we age. After B, yeah, we age at room temperature or slightly elevated temperature. And then we pull again and we find there's another increase of hardness with the upper and the lower yield, the limit, and another formation of a Lüders band. So what happened in the aging? In the aging, we have diffusion of the carbon atoms within the crystal lattice, and so time, diffusion time, and maybe temperature. Carbon goes interstitial, so it goes fast, relatively fast. So the carbon moves back to the dislocation. Here, if you do nothing, immediately unloading and loading, there is no time for precipitation, for segregation of carbon to diffuse. There's no diffusion time to go to the dislocation. But if we do aging, yeah, we make it old, we wait. If we do the aging, then the diffusion time becomes important, the carbon moves back to the new locations of the dislocations. So here were the old positions of dislocations. Then we move the dislocations. We age here. During the aging, the carbon goes to the new locations of the dislocations. And then we start with the Lüders band again. So that's also a nice strengthening mechanism. After plastic deformation, we do the aging, which can be a slightly elevated temperature to enhance the diffusion a little bit. And then we have the solid solution hardening, telling that alloys in solid solution, for example, are usually stronger than pure metals of the solvent. And this is because we have either interstitial, like carbon, or substitutional impurities in a solution, and they cause the lattice strain. The carbon interstitial widens or compresses the surrounding lattice because it needs space by itself. And if you put other interstitials, the same thing. If you put it's a bigger effect. Or if you put a big atom, gallium, into iron matrix, then it expands locally the lattice. Yeah, if there's a vacancy moving to the big atom, then the probability is that the big atom, the vacancy moves back again, and the big atom to its original position because of the surrounding strain fields. So these solutes, they cause lattice strain. And as a result, the impurities interact with the dislocation strain fields and hinder dislocation motion, like I explained the slide before on carbon and the Lüders band. The impurities tend to diffuse and segregate around the dislocation core to find atomic sites more suited for their radius. So the large atoms, large substitutional atoms, they may go where in the tensor, in the positive strain, lattice strain areas. And if you put smaller substitutional atoms in, they may go into the compressed areas, where the lattice parameter wants to be a little smaller. So they adapt whatever is suited to the atomic radii. Don't put the same atomic radii in. You can put that, then nothing happens. Isotopes. So this reduces the overall strain energy and anchor the dislocation. If I want to move the dislocation, I have to overcome this barrier, or with diffusion move the whole thing, drag the whole solvents through. Solutes. Sorry. So motion of the dislocation core away from the impurities moves it to a region of lattice where the atomic strains are greater, i.e. the dislocation strains are no longer compensated by the impurity atoms. So here, smaller and larger substitutional impurities tends to diffuse into strained regions around the dislocation, leading to partial cancellation of impurity dislocation lattice strains. So here you see these are the lattice distortions as we had them in the diffusion cores. This is small substitutional, so it wants to have a smaller lattice parameter, which is in a compressive strain field, compressive stress field around the dislocation. And here is a larger one, so it wants to have a larger lattice parameter, and that you find, that larger lattice parameter you find in a tensile stress field around the dislocation, so below the dislocation. This is a vacancy, and this is the interstitial. Interstitial also wants to push, so needs more space, so it goes into an area where I have already tensile stresses. And what's here? Well, they put 2 in here. So single phase, we can have the point defects. You see the strain fields here a little exaggerated for big one. And a similar size one. So if you put a similar size, I don't know which metal they put into what, maybe into iron, I don't know. Percent alloying element, you see zinc has a small difference, so it's relatively flat. Beryllium makes it very small, so you get a large strain field which interacts strongly with the dislocation. Then the yield strength increases a lot with the alloying concentration, and for this situation it's intermediate. Yeah, it also says it depends on the difference in the size between the solute and the solvent atoms, and of course the amount of solute you add. Another figure here about the strength, the hardness, ductility, electrical conductivity, and the creep resistance. So this is percent zinc in copper. Here we have it. It's copper, yeah. Solid solution strength and alloy. The increase in percent elongation is not typical of solid solution strengthening. So here we see the yield strength, we see the electric conductivity goes down. Why does the electric conductivity go down when I add zinc into copper? Because electric conductivity is motion of electrons. Electrons are waves. So electron waves, and when they hit a zinc atom, they get scattered. They're not going continuously homogeneously through the crystal lattice. They get scattered from the one zinc atom, and scattering means in all directions, not just in the forward direction, also in the back direction, and that's some resistance. So electric conductivity, you get electric resistance which goes up, or conductivity is 1 over resistance which goes down. So scattering of electron waves by the solute atoms, zinc, gives scattering, and therefore they may be backscattered. So not going, instead of going in the forward direction, they go in the back direction. Against the electric field, then they have to turn around and accelerate again. So electric conductivity goes down, but the yield strength goes up, tensile strength goes up, and the percent elongation also goes up. So it's always physics, nature, engineering, there are always compromises. Conductivity goes down, but the mechanical properties go up. So when the solute exceeds the solubility limit, then we get 2 phases. We know that already. And we can have the following situations, or the many situations here. So we can hard precipitates in soft matrix, or soft in hard, and then we can have the spheres, or we can have the needles. So on the right hand side here we have poor mechanical properties, on the left hand side we have good mechanical properties. Poor because here at the tip of the needles we have stress concentrations. Stress concentrations, they may lead to cracking, yielding and cracking. So this becomes poor. Also, if the included material here is soft, you see the crack can go through like that. If it's hard, then the crack would be held by the hard material. So if the crack goes through here, it just goes through the soft material. But if here a crack goes through the soft matrix, it may hit a hard precipitate, and that makes the properties better. Or here we have the size of the precipitates. So we have good properties if we have small precipitates and many of them, as compared of large precipitates and not so many. Or if you compare this, more precipitates may give you, of the same size, give you good properties rather than just a few precipitates. Okay, so this is now the last chapter on the strengthening mechanisms, namely putting composite materials. Composite materials is we take layers, the materials we build up in layers. So here are the individual layers of one material, white material and gray material, white material and gray material and white material. We can bake them together, glue them together, bond them together by intermetallic, by bonding, by rolling, by the various fabrication methods. And then we can have the two situations. Either we apply a compression or tensile stress perpendicular to the stacking, so along the normal of the stacking, or here parallel to the stacking, so in plane to the stacking or perpendicular to the plane of the stacking. That leads to the Voigt model and the Royce model. And these models, they are shown here. So the strain in the Voigt model is when I strain the material, when I stress the material and strain it vertically here by these arrows, then of course the two strains have to be the same. Yeah, if I compress the white material, I also compress the gray material by the same amount. And this is epsilon 1 equals epsilon 2 equals epsilon. And then I can put up the stresses. So sigma 1 equals E1 times epsilon 1 and sigma 2 equals E2 epsilon 2. I can calculate the forces, yeah, by considering the area for the 1 and for the 2. And the total force has to be F1 plus F2. So I get a average elastic modulus, which is the applied stress, so the average applied stress divided by the epsilon, which is given there. And then I can put all these formula together and get the apparent elastic modulus is F times epsilon 1 plus 1 minus F times epsilon E1 plus 1 minus F times E2, where F is the fraction of the two material. So how much white material and 1 minus is how much the gray material I have. And in the Royce model, I apply the stress perpendicular to the planes. So then, of course, the sigmas are the same. So here we had the epsilons the same, but each layer had a different stress. Here I push, they all have the same force on the same area. So the sigmas are the same, which is the sigma average, which is just P over A, so the force over the area. H is the layer thickness here somewhere, okay. And I can work it out. Then delta H is H1 epsilon 1 plus H2 epsilon 2 for one bilayer and express it by the elastic modulus, so sigma 1 over E1 and sigma 2 over E2, and then I can calculate an epsilon, a strain epsilon, average, yeah, delta H over H1 plus H2, so over one bilayer, and get eventually this formula F times sigma applied over E1 plus the fraction of the gray phase 1 minus F times sigma over E2. So eventually I get for the Royce model 1 over E average equals F times over E1 plus 1 minus F times 1 over E2. So here in the void model, figure there, we get the average of the E1 and the E2, and in the Royce model we get the reciprocal averages, or the reciprocal average over E1 and E2. So that's the salient difference between them. Just get familiar with the formula. There also may be a tutorial and a homework for it. If we look to the strengthening mechanisms of composite materials, then here this is the void behavior. So in the void behavior we have the volume fraction and the shear modulus here. Volume fraction is F, yeah. So void is here. It's just a linear behavior. So E is linear behavior in the volume fraction. And here E is somehow related to the reciprocals of it. So if you solve it to E, then it becomes this model. Royce model is compared to the void model. And then there exist other models like the Hashine Stringcham bounds for G with Poisson ratio 0.3. So we haven't put the Poisson's ratio in, we haven't put the shear modulus in. They play a role, of course. If you compress here, you also get a lateral expansion due to Poisson's ratio. And this is different in the white and in the black layer. So that is where Poisson's ratio plays a role. And then when you have a difference in expansion between the white and the black, then you get a shear between the white and the black. And that's where you get the shear modulus in. And that gives you two boundaries closer to the void situation. So the void situation, you compress here and you widen laterally. But when you compress, you may also get shear stresses because you have different elastic moduli at the layer. So you get a higher and you get a lower boundary in this diagram by Hashine-Stringcham, which lays between the void and the Royce. So the conservative models is without shear modulus and without Poisson's ratio, and if you do it more properly, you get this inner lens here. With this, I conclude the lesson on plastic deformation with dislocations. We will hear more about it, we will apply it here and there, but next time we come to fracture of materials, or maybe the next few times, and then we come to creep of materials, where dislocations also play a role. So please prepare it well. There's some homework, there are some tutorials, and catch you later. Come to the office hour. Let me know when you want to meet me. Bye.